Ever wondered how a robotic rover can survive Mars? Let's break it down and how it survives millions of kilometers away from Earth. The concept of a rover surviving on a planet with conditions that are vastly different from Earth might seem impossible, but NASA's Curiosity and Perseverance have been navigating the Martian surface for years. These rovers are designed to withstand a range of challenges, like extreme temps and more. Their survival is a result of remarkable engineering and innovation of tech that allows them to operate autonomously, despite being located 225 million kilometers from home. By understanding how these rovers manage to survive on Mars, we gain insight into how we can explore distant planets, but also how technology can adapt to seemingly inhospitable environments. The Mars Rovers, such as Curiosity, landed in 2012, and the Perseverance in 2021, are part of NASA's mission to explore Mars. These rovers are equipped with an array of scientific instruments designed to study the atmosphere, geology, and potential signs of past life. Each rover is tasked with a specific set of objectives. Curiosity is aimed to assess the past habitability of Mars, while Perseverance focuses on the search for ancient microbial life and samples. These missions are critical for understanding the potential for life on Mars and the future of Earth. Understanding how Mars rovers survive is crucial not only for the continued operation, but also for future space exploration. If we have to send humans to Mars to establish outposts, we need to learn how to create tech that can endure the harsh Martian environment. This innovation is tested by rovers today and may one day be adapted to human missions. Mars presents one of the most extreme temperature environments in our solar system. The average temp on Mars is a frigid -80 Fahrenheit, but can vary drastically. At the equator, daytime temps can reach up to 68 degrees Fahrenheit, but at night they can drop up to -195 degrees. These temperature swings create a unique challenge for Mars rovers, whose internal components are vulnerable to freezing and damage. Curiosity has a thermal system in place to maintain the rover's temp within a safe operating range, using a combination of insulation, heaters, and onboard temp monitoring systems. Mars' atmosphere is over 100 times thinner than Earth's and consists mostly of carbon dioxide with very little oxygen. The thin atmosphere not only is incapable of supporting life, but also offers very little protection from the sun's radiation or impacts of meteors. For the rovers, the thin atmosphere means there's minimal air pressure, which complicates cooling. Air-based cooling systems, such as those found in many Earth-based vehicles, are ineffective on Mars due to the lack of sufficient atmospheric density. As a result, the rovers must rely on passive dynamic controls for temperatures, such as insulating materials and heat-conducting components to regulate temperatures. One of the most unique and dangerous features of the Martian environment is the dust storms. Mars experiences massive dust storms that can engulf the planet, sometimes lasting for months. These storms reduce visibility and significantly affect the rover's ability to recharge batteries, especially powered by solar panels. For example, the Opportunity rover, which relies on solar power, was hit by a global dust storm in 2018, which led to eventual loss. Dust accumulation on panels can also reduce efficiency, meaning the rover could struggle to gather power to function. In response to this challenge, the Curiosity and Perseverance rovers use nuclear-powered radioisotope thermoelectric generators, which are not affected by dust storms. The question of how to power a rover on Mars is critical given the planet's weak sunlight. For the past few rovers, including Spirit and Opportunity, solar panels were the primary energy source. These panels relied on sunlight, which in turn powered the rover's systems. However, the weak Martian sun combined with dust storms made solar power less reliable. For example, Opportunity experienced difficulty maintaining power during dust storms, leading to failure. In contrast, Curiosity and Perseverance use nuclear power through the radioisotopes. These systems convert heat from the natural decay of plutonium into electricity. This technology ensures that the rover can operate year-round without fluctuations or downtime. The rovers need to store energy to survive the cold Martian nights, though, which can last for hours. For solar-powered rovers, batteries are used to store the energy generated during the day for use at night. However, these batteries are only effective at the rover's solar panels can collect enough sunlight to charge them. Rovers with RPS systems like Curiosity and Perseverance don't need the sun for power. Their energy is continuously supplied by the nuclear power system. Nonetheless, these batteries in the rovers still serve a backup role, ensuring that the rover's internal system can be powered up during brief periods where the power system requires maintenance or recalibration. The vast distance between Earth and Mars, ranging from 13 to 24 minutes for signals to travel one way, creates significant communication delay. This time lag means that Mars rovers must operate autonomously, executing demands sent in advance, rather than real time. To manage this communication challenge, rovers rely on orbiters such as the Mars Reconnaissance Orbiter to relay signals back to Earth, ensuring continuous data transfers. Mars' extreme temperatures, averaging at -80 degrees Fahrenheit, requires rovers to have self-protection systems like insulation and heaters to keep internal components operational. Rovers enter sleep mode during the cold Martian nights to conserve power, and onboard diagnostics monitor health. Rovers also use sensors and cameras to navigate autonomously, detecting hazards and selecting paths. Mars rovers face frequent dust storms, and dust accumulation on panels and cameras can hinder functionality. To combat this, rovers like Curiosity's use wind and vibration-based systems to clean dust off components, while Perseverance employs dust-repelling coatings. The rover's design also minimizes dust impact. In cases of heavy dust buildup, rovers can enter safe mode, maintaining power. Mars is a frigid planet with an average surface temp around -80 degrees Fahrenheit, but temperatures can fluctuate. These extreme variations pose significant challenges for Mars rovers, as many of the components are vulnerable to freezing or overheating. To combat this, rovers are equipped with advanced thermal systems and maintain operational temperatures for the rover's electronics, batteries, and scientific instruments. One of the primary components on these systems is insulation. Rovers like Curiosity and Perseverance feature layers of thermal insulation that shield sensitive parts from Mars's intense temperatures. Additionally, electrical heaters are strategically placed around critical components to prevent freezing. For example, the rover's batteries, which store energy to use during the Martian night, are equipped with thermal blankets and heaters to keep them at optimal temperatures. The rover's mechanical design must be robust enough to handle Mars' harsh physical environment, including dust storms, high winds, and extreme temp fluctuations. The rover is built to endure the relentless dust storms that can sometimes last for months and reduce visibility, while also dealing with high winds that could affect its mobility and integrity. To ensure it can navigate the surface safely, the rover's wheels are constructed from durable materials and designed with treads that can grip the rocky Martian terrain. For example, Curiosity and Perseverance both use specially designed aluminum wheels with built-in shock-absorbing elements to withstand impacts in rough terrain. In addition to dealing with high winds, the rover's mechanical design also accounts for dust accumulation. Dust storms on Mars can be intense, with particles fine enough to penetrate even small openings. As mentioned, self-cleaning mechanisms and dust-resistant coatings are employed on crucial parts like solar panels, sensors, and cameras to prevent dust from clogging them. The rover's body is sealed to prevent dust from entering into internal components, while high-pressure systems help ensure that vital areas are protected. The rover's ability to endure these high-pressure situations is integral to its longevity and ability to continue functioning throughout the mission. To survive on the surface of Mars, rovers like Curiosity and Perseverance rely on an array of innovative tech. From thermal systems that protect the rover from freezing temps to mechanical designs that ensure durability against dust storms and high winds, these technologies are critical for the rover's survival. Autonomous systems, self-cleaning mechanisms, and the use of relay satellites also play significant roles in ensuring continuous communication with Earth, even when the rover is out of direct sight. Together, these strategies allow rovers to not only survive, but thrive on the Red Planet, providing scientists with a wealth of data that can be impossible to gather otherwise. Mars exploration is a thrilling point, with new discoveries and advancements happening all the time. The potential of Mars rovers in such a harsh environment is a testament to human ingenuity and the potential for future breakthroughs.